Hello, welcome back to our discussion of wavelets. So this is part 2 of continuous wavelet transformations, and we'll discuss how we actually do a wavelet transform. And there's another lecture to follow on the discrete wavelet transformation. Just like there was a Fourier transformation, and then we talked about the discrete Fourier transform, so the same is true with wavelets. There's continuous wavelets, which we'll talk about today, and then discrete wavelets, which is simpler in the sense when you're finally done, easy to compute, but a little more subtle how you get there. We'll talk about that next time. So today we'll get to the real basics of wavelets. And as you can see by looking at what we have to cover, we'll start off by talking about short-time Fourier transforms, precursor to wavelets. Then we'll talk about continuous wavelet transformations, talk about how you generate the whole basis of wavelets. We'll do a visualization of the application of wavelets, and then we'll send you on your way with an implementation, computer code, to let you try out some of these new ideas. So again, this is a new subject. I appreciate that most of you have never seen it before, so we're really trying to get you with your feet on the ground by working with wavelets. So let's go ahead. Recall, this is our problem. We have a signal, a non-stationary signal, in which we have a number of frequencies which exist at different times. And we're trying to develop an analysis tool which will be sensitive to which frequencies are present at which time. Now, the usual Fourier analysis uses sine omega t, cosine omega t, sine 2 omega t, cosine 2 omega t, etc. But since all these functions exist for all times, they overlap with each other for all times, and therefore they're correlated. We've talked about that already, but because they're correlated, they have dependent components. So each component depends on another, and you just can't throw out one without affecting them all. So if you throw out one component, you really need to redo the whole analysis, which is very inefficient. So we'll get away from that. One of the precursors of wavelet transformations, one of the ways people got away from the shortcomings of Fourier analysis, is known as the short-time Fourier transform. So you do a Fourier transform in a short time interval. So these colored boxes, which were there previously just to help you visualize the problem, now have some meaning. And what it means is, okay, if this was our signal, then we would do one Fourier transform in the yellow box. Then when the signal changes, we would do another Fourier transform for a short time, covering the green box. And finally, when the signal changed again, we could do a third Fourier transform. So these boxes given in the pictures is what mathematically might be called a window function, or figuratively are just windows placed over the data, so we'd look at just one little part, or one limited part anyway, of the data. So when we're done with the short-time Fourier transform, what we have is a bunch of Fourier transforms, each one of which has a center, place where the window has been placed, at a different time. So if you look at this now, what we're saying is, basically it's a Fourier analysis. Omega, the usual frequency, it could be discrete, continuous, but we have different times at which we're doing the analysis. So the transform is now a function of omega and a parameter, which is really just another variable, the time at which we've placed each window. So you shouldn't think of this as saying it's a function of all time, it's a function of the window placement time, but it's still transformed in omega space. So putting all these ideas into mathematical expression, we're left here with the equation of the short-term Fourier transform is the function of omega, omega being the usual frequency, and tau being the center. Here's tau 1, tau 2, tau 3, where we place the window. So it's an integral, as before, over all time, plus or minus infinity, e to the I omega t. Maybe it's a normalization constant I'm leaving out. And the new part here is this window function. Okay? Then that's just sweeps through the data and says it's at, the window function has its maximum at time 0. So as we vary tau, we get to place the window at different places along the data. And this is our signal at the end. Okay? So a tau here is a variable or a parameter. So we take the Fourier transform for all possible values of tau as well as record it to get all frequencies out. Okay? So now we can get on to the wavelet transform. So look next, slide 42. This is the real wavelet transform. So in the wavelet transform, we start off thinking of a Fourier transform. We get where we have our transform capital Y of omega. And the Fourier transform involves a basis function, e to the I omega t, the exponential. In a wavelet transform, we'll again call it capital Y. We again have one variable, s, a scale variable, we'll talk about that, corresponds to the frequency variable. And we have this other variable, tau, which is time-like, but it's really the place where we put the window function. And rather than integrating over an exponential as we do with Fourier analysis, we're now integrating over a wavelet, lowercase psi, and that has both the scale parameter s in it and the tau parameter, and it's a function of time. So there's a lot of parameters there. There's no question about that, and that's what we try to make sense of today. So here we have 3 possible wavelets. Each of these are mother wavelets, as we'll see. So the actual wavelet transform is now, as we promised, it looks just like a Fourier transform, integration over positive to negative infinity in time, all possible times. But that means something now because the wavelet, which occurs right here, is limited. It's a wave packet, so it only covers a short time. So effectively, it's just an integration over that period of time over which the wavelet exists. The function, our signal, y of t here, can be over all possible times, but this is not, we have a window function built into the wavelet. Okay? So it's very similar to a short-term or time Fourier transform. The window is now localized. The window function is now present in the wavelet because the wavelet is localized in time. So it's its own window. We don't need anymore a separate window function. Because every wavelet, as you see here 3 examples, every wavelet oscillates, that means every wavelet contains a range of frequencies. Because they're finite in time, that oscillation is not never just one frequency. It must be a range of frequency. So we know they have a range of frequencies in each wavelet. And so what capital Y, what the transform represents, as always, it's the amount of, or the correlation of, a wavelet present in the signal. Okay? Just like the Fourier transform gives you the amount of e to the I omega t present for any value of omega, so the same is true here. It's the amount of any wavelet in the signal. That's what a transform is. Tau, which is the time interval over which the wavelet exists, or the center where we place the wavelet, is a parameter. So we now have a doubly indexed transform. So it's better to do on a computer because you can't just plot it up as a function of one variable. You need a surface plot, function of s, the frequency-like variable, and tau, where we place the window. S is called the scale. Remember, you know the word scale, maybe from fractals or just from maps, large scale, small scale, little high scale where we see lots of little numbers. And think of the scale as 2 pi over omega. So omega is our usual transform frequency variable, and we could use that still, but scale is usually used. And that has, for good reason, because we're thinking of digital pictures like we played with before. We have various scales. We're thinking of different sizes. So scale is really good for size, and here the frequency is in some spatial object. Okay? So that's what scale represents. So if we're talking about a signal in which we have lots of little wiggles and oscillations, we need to see a lot of details. That means we need to see the signal at small values of the scale. We need a good small scale analysis. To see that, to see lots of oscillations, we need to see high frequencies. That's right. So the scale is inversely proportional to the frequency. You want to see little bits and pieces, then you need high frequency, you need small scale. Okay. So let's go ahead again and say, okay, we need now wavelets for all different scales and all different times. So let's look at slide 49. What do you see here? Well, you see here a very clever way of getting wavelets at all possible scales, or frequencies, and covering all possible times. So we have on the left here in the blue bar, we have a small psi, and on the right we have a large case, uppercase, capital psi. So capital psi is called a mother wavelet. Small psi is called the daughter, if you want son, but usually it's daughter wavelets. And we see that the daughter wavelet is a function of time. Okay, it's just a wave packet, but it has some value of scale. It has some value of tau, where it's placed. And so you take the mother wavelet and you just evaluate it at t minus tau over s. And since the wavelets all are peaked usually at 0, well, that's the largest part, putting tau in there and subtracting it just shifts it, translates it to some time. So time t, or tau, tells you where the wavelet's been translated to. And then by dividing by the scale, which is the same dimension as time, okay, so divided by the scale is like 1 over the frequency. We can shrink the wavelet up, or shrink its time dependence up, or we can expand it. So, to see what we mean, here we have that one wavelet, just that little oscillatory pulse, and this is what it looks like for a scale value of 1 and tau of 0. It's at the origin. If we keep it at the origin here in green, we look at tau 0 still, but we change the scale to 1/2, we see that we're looking at a smaller scale, more oscillations. We've made it a higher frequency. Very neat. Or we could take the same wavelet, not change the scale at all, but just evaluate it at a tau value here of 6 rather than 0. That just translates it to its center here at 6 as its peak. Okay, so, or we could do both. Here we can change the scale to a larger number that stretches it out, and here we're keeping it still at tau 0, so we see it in the same location as before, but stretched out. So it's very easy. We just have one wavelet, the mother, and we stretch it, compress it, translate her, like a good soccer mom. She goes every place and, is flexible. Okay. So psi is called the mother wavelet. Notice that there's a fixed number of oscillations in our example here, but for all of them in the wavelet, and therefore when we compress it or scale it, we obviously change the frequency. S values less than 1 correspond to high frequencies. S values greater than 1 correspond to low frequencies. It's, as I said, it's easier to think of it just in terms of scale of a figure, details. So large S corresponds to large scale. That's the general shape of an object. If we want to outline what the object is, we just say, okay, it's like this. It's broad shape. It doesn't need too much information. So you don't need to store a lot of data, a lot of information about large scale, because once you get the general shape down, you got it down. You don't need more information on that. Small s, however, is interesting because small s is where the details are. And so the more information you give me about the small s character, the more details I have, the higher a resolution picture I can construct of the object. And there we've said it. So this was the gadget on the camera. How do we change the resolution? Changing the resolution is how many small s details. If you tell me I'm going to print this up on a postage stamp, I don't need many details. I don't need all those small s numbers. You just throw them away. The big S stuff doesn't change. It looks just as good. Okay? If I want all the details, then I need more small s. So this is it. So let's visualize. Let's figure out, give you a visualization of how this works in practice. Look at slide 54, please. Now, I'm not emphasizing the mathematics of Fourier transforms and wavelet transforms here. So, it's very similar, though. And as we see here, we have two equations. In red, we have the definition of the Fourier transform. Of the wavelet transform. And you see there's a normalization factor 1 over the square root of s. Some texts, some books, some papers may use a different normalization. Whatever it is, you have to be consistent. So that here, for example, when we come back and we actually do the mathematics for the inverse wavelet transformation, we have an s to the 3/2 power, and that comes about because we have a 1 over square root of s here. And these normalizations are often chosen to give the same amount of power for different components, to balance things off. And c is just some constant, some normalization constant, which depends on the wavelets being used. People often forget about it because it's usually the relative strength that matters. So, again, in red, the wavelet transformation. We have a signal here, y, of t. That's what you've measured. And now we integrate over it with some mother wavelet, capital Psi, and by evaluating it at this scaled and translated, and then evaluating the transform for all possible values of s and for all possible values of tau, scale, and time, we get a two-dimensional space of the transform. Very nice. And if we wanted to invert it, what does inversion do? Well, if we wanted to invert it, then we would integrate the transform over all scales and over all tau values. What about inversion? Well, that, of course, is what goes on in your digital camera when you look at the picture. Now we're getting down to that, why the camera is so important. When you take a picture, do you remember one of those settings, the one all the way at the top, said RAW? That gave you all the data that was measured, every little pixel element. That's called RAW, usually RAW or complete. That's a huge amount of data, and they immediately transform that into a wavelet analysis. They do the transformation. They compute all the wavelet coefficients, S and tau values, and that's what's saved. And then whenever you want the picture, it's reconstructed essentially in this way. So unless you want all the raw data, what you're seeing almost all the time, for example, the JPEG, is a wavelet transform of whatever resolution you want, as many data as you want. So this really is the method being used. How does that actually work in practice? So here you see in beautiful turquoise and dirty yellow a chirp signal. That's sine of 60 t squared. So it's like a sine function whose frequency gets higher and higher in time. And the way the wavelet transform is computed, remember it's a two-dimensional object, is first we have our signal and then we convolute it, which means we just multiply it and integrate over all time by a low scale, which means small, a small scale wavelet. So here's a wavelet. It's one of the famous shapes we'll talk about. You'll see again, but it's just an oscillatory function. And we multiply it and we integrate over all time. We get a number. Then we move that wavelet along, translate it, and we get another number. Okay? So that's one value of S, and we're now evaluating the different tau values. And then until we're finished covering the whole signal, we get all tau values. Okay? So that gives us one row or one column in the transform. And then we say, okay, that gives us all the high resolution information we want, let's say, if that's the smallest. But now we can expand the scale in yellow here, and now do the same thing, convolute it with the same signal. Down below here, the signal doesn't change, but the wavelet is a stretched out one. Then we translate it along till we cover the whole signal, and we repeat the process. So we start at a very small scale, get all the numbers for traveling around, increase the scale more and more, and then we can either save them all or we can throw some out. So next time we'll talk about how you throw them out. So here, it took a while because there's a lot of information which just suddenly came up. Here's the result of such an analysis. This, recall, is our original signal. 3 boxes, 3 functions in time. And now, down here, we have in yellow, so let's see this comes out of the computer program. So this is the input, the solid line. So the solid line is, in fact, the same as we have up above. It's the signal, and then the dotted line is the inverse transform. So that's how you reproduce the signal after throwing out bits and pieces. Not every part is here, but we see, oh, this does a pretty good job at reproducing the signal. There's a little differences here, a little differences there, but that might almost be due to how we're plotting it up. If we look now in this green area, we see that we have a surface plot. And what's this a surface plot of? Well, it's a surface plot of capital Y. This is the wavelet transform. And it's capital Y as a function of the tau, the time translation variable, or time, and S, the scale. And S, recall, is proportional to 1 over the frequency. Okay? And if we look now at very short times, we see, oh, at very short times, there wasn't much going on. There was maybe one peak here, and that's it. So at the lowest times, there was just one frequency present. As time increases, we move along here, we can see, oh, there's 2 peaks. Oh, yes, that's this region in green where we had 2 peaks going. And if you rotate this just right, you could get the relative strength of the 2 peaks corresponding to what we saw before. And then we see at the largest times here, there's 1, 2, 3 peaks in the Fourier transform. That corresponds to the pink region where we had 3 frequencies present. So that's not to say it doesn't take a little bit of learning to be able to read these graphs, but it's more information, the whole new dimension of information. That's the Fourier transform. It really works. And then if we take all these data here, transform it back, it reproduces the signal. Okay? So this is good. You should believe me, it's true. But now we need to set you to work. Okay? So that's what we'll do in the implementation. But some of you may be the mathematical type, and I've really sloughed over the mathematics. And there is mathematics here. In order for these transforms to work, the mathematics has to be solid, and we know how to do that. But it's a developing field, so people have sort of defined the math as needed in order to get the concepts to work. First, we're dealing with we deal only with real wavelets. The signal can be complex, but let's say the wavelets are always real, just to keep the analysis simpler. And the wavelets must always oscillate. So I've said that before, the wavelets are always oscillating, but now we're being more specific. We're saying they oscillate such that if you integrate the wavelet over time, all time, you get 0 as its average. So as much as it is above, it has to equally be below. Then we're saying, okay, the wavelets also must be localized, making them a wave packet, so that if we integrate over all time again, and we integrate the modulus of the wavelet squared, doesn't really need a modulus sign here because it's real anyway, but it could be plus or minus, so that still would be positive. Anyway, that's how it's written. So the modulus squared also must be finite. That means it's square integrable. So in the first case, the average vanishes. In the second case, any number is fine. And finally, in order to get this not too sensitive to all the details, we have the first p moments. P is a number, small number, which each case defines, of the first p moments of the wavelet must vanish. So time to the 0th power times the wavelet over all time, time to the first power, time to the p minus 1 power, all of those must vanish. So recall, the integration of the wavelet by itself vanishes, it oscillates, and this says that the first, if you make a polynomial, for a small number of p, small value of p, they also, all those moments must vanish. Okay? So they're all quite oscillatory, they vanish over time. So finally, here's your assignment. Time for you to get your feet on the ground and do something. Take your DFT program, or your CFT, and convert it to do a wavelet transformation. Okay? Do the same ideas, just examine it. You know. So look at it, derive the program such that you can use 3 different wavelets. And we give you the equations in the textbook. One is called the Morley, the other is a Mexican hat, that Gaussian one, and a Dahar wavelet. Okay? So try out 3 wavelets. They're just subroutines. Shouldn't change your answers much, but it will somewhat. And then test out your transform. To do this, doesn't have to be very precise or very compact now. We just want to make sure you can get the basic ideas right. Try your wavelet out first on a sine wave that extends over all time. You should have no time dependence. In the wavelet, it should be the same for all time. Then try it on a sum of 3 different frequencies. That means you should see 3 peaks, 2, 4, 6. They should differ by 1, 2, 3, and the heights in that proportion. And finally, try it on our non-stationary signal, which we used as our example. Okay. And then you should also get as we've shown you. And finally, see if it works. See if you can invert your wavelet back and get the input. The normalization factor doesn't matter. If the shape is right, normalize at one point and use that as the normalization constant. See if you can reproduce your input. So, that's your homework, okay? Try this out. Convert a program you had to use wavelets. Try the 3 wavelets we give you, a new basis function, and now do the Fourier transform, but you have that extra variable. You do it for not just frequency, which is 1 over scale, but you also do it for this Tor variable. Okay? So, that's it for today. Next time we'll talk about digitizing this, making this more discrete, but we've covered the basis of wavelets. You should understand that all now. Bye-bye.